Now today we're going to be working on a chi-square test, but this time it's not going to be a chi-square test for goodness of fit. We're going to be using the chi-square with a data set involving two-way tables, and this particular test is going to help us work with hypothesis testing for test for homogeneity and also for the test for independence. But for this specific lesson or case, we're going to be using the test for homogeneity, and basically the two different tests, homogeneity and independence. The procedure on finding the p-value and the test statistic is just pretty much the same. It's just that there is a difference on how the data set were presented on each case and how it's being used in performing hypothesis testing for a categorical variable. Now for this particular case, we're going to be working on the case of healthcare system for Canada and the United States. So for our first work, we're going to be working on this word problem, and the word problem says that Canada has universal health care. Now the United States does not, but often offers more elaborate treatment to patients with access. Now, how do the two systems compare in treating heart attacks? So researchers compared random samples of US and Canadian heart attacks patients, and one key outcome was the patient's own assessments of their quality of life relative to what it had been before the heart attacks. So here are the data for the patients who survived a year. So they asked people or patients in Canada and the United States, and they have 5 categories on their survey, and we're going to be using this specific data set in finding or working on a significant test. And the question is there a significant difference between two distribution of quality of life ratings, or the quality of life ratings based on our given data set? So we need to carry out an appropriate test for this particular data set at alpha of 0.01. Now to see if this is a test for homogeneity or test for independence, we're going to be focusing on the sample, and in this particular case, this one is an example of test for homogeneity because we have two randomly selected or two independent random samples, and it's mentioned here in our problem wherein the researchers compared random samples of US and Canadian heart attacks patients. So we have two different samples from different countries, and they're both, of course, independent. So if we're going to take a look at the graph of the respondents in Canada and the United States, we'll be able to see that with this particular graph, there's not much difference that we could see if we're just going to rely on the histogram for the respondents in Canada and the US based on their quality of life survey. So to work out this particular problem on statistics, we're going to be working on a hypothesis test to see if there is a significant difference between the two groups of respondents. So to go back to our hypothesis testing, the first thing that we need to do is to work on our null hypothesis and alternative hypothesis. Now in word problems like this, you need to look at the questions itself, and it's most likely going to be asked at the very on the latter part of the case study that you're working on. And in this particular case, we're asked to find or if there is a significant difference between the two distributions of quality of life ratings based on our samples. So that will be our clue on writing out our hypothesis. So for this one, our null hypothesis will be that there's no difference in the distribution of quality of life for patients who have suffered a heart attack in Canada and the United States. And our alternative hypothesis is going to be that there is a difference in the distribution of quality of life for patients who have suffered heart attacks in Canada and the United States. Now we're going to be testing this hypothesis against the alpha of 0.01 or 1%. And the next procedure that we're going to be working on will be the conditions for our hypothesis testing. And just like any hypothesis test, we need to work on our conditions for normality, for independence, and the random sample. So going back to the first paragraph in our case, wherein we'll be able to find the information that we need for our conditions, starting with the randomness of our sample. And in this case, it is specifically written in our case that it came from independent random sample. So this particular condition is now satisfied. Now for the second condition, we're going to work on the 10% rule or independence. And in this particular condition, we know that the random or the samples were randomly selected and they're both independent. But if we're going to base it on the parameter, the population of interest will be the patients who suffered heart attacks in Canada and the United States. And our first parameter will be that all Canadian heart attacks patients, and our sample of 311 based on our survey is going to be our small letter n that we're going to use for the 10% rule. So in this case, big N is indeed greater than 10 times the sample size, because we know that it's going to be bigger than 10 times of 311, which will be 3,111. And for our second parameter, which will be the US heart attacks patients, the big N or N sub 2 would be bigger or greater than 10 times the sample size of 2,168. So in this case, the 10% rule is also satisfied. And for the last condition, which is large count, conditions for large count, all we need to do is to find or compute for the expected value for each category for the two samples, and all of them should be greater than or equal to 5. Now to do this, we're going to be using our calculator. So we're going to go back to condition number 3 after we have computed for the expected value for each category for the two columns that we have. So going back to our observed data set, which is the given data, to find our expected value, which is the calculation part of our test, we know that we're working on chi-square test for homogeneity, and to work with expected value, we have a formula that we need to follow, and the formula for the expected counts for test for homogeneity is as follows. So for each category for the two columns, the expected count is given by the formula row total times the row column or column total all over the table total. So in this case, only the column total is given in this problem, so we need to compute for the row total. So all you need to do is to add 75 and 541, 71 and 498, and in this case our row total will be as follows, and we're going to use that to find our expected counts. So for the expected counts, we need to construct our table for test for homogeneity. So we'll have an organized or a more organized table for the expected counts or expected values for each column and each category. So we're going to start with the first category, which is much better, and we're going to compute for the expected value for the first column, which is Canada. So using our formula, all we need to do is to multiply 616, which is the row total of row 1, times 311, which is the column total of column 1, which is Canada, divided by the total of the table, which is 2,476. So for the first category under Canada, we have 77.37 as its expected count. And we're going to do that on the second category. So we're going to be multiplying 569 and 311 divided by the table total of 24 or 2,476, which gives us 71.47. And then for the third category, we're going to do the same thing, which is equal to 109.91. And if we're just going to use our calculator and continue working on the first column and follow it with the second column, our table will have 41.7 and 10.55 for the expected values for our sample in Canada. And for the sample for the United States, we're just going to use the same formula, and we'll have 538.63, 497.53, 764.09, 290.3, and 73.45. Now, we're seeing that all expected values for Canada and the United States against row 1 to 2, 3, and 4, and 5 are all greater than 5. So going back to the conditions a while ago for large counts, we can now say that all expected counts is greater than or equal to 5. So just go back to your conditions and just write that all expected counts is greater than or equal to 5 to verify that all three conditions are satisfied. So it's safe to use the formula in finding the p-value and the test statistic for this particular hypothesis test. So now that we have our two tables, we have our observed table and the expected values for the other table, we're going to be using our calculator to compute for the test statistic and the p-value so we can generate our values. So let's go ahead and use our TI-84 to plug in table 1 and table 2 to our matrix. So remember, we have table 1 for the observed value, which is the given values in the problem, and we have the computed expected value. So all we need to do is to go to second x to the negative 1 for the matrix and go all the way to edit, and we're going to define 5 over 2. So I have encoded all the values in my table, but I'm going to show you how the calculator works for this particular computation. So you need to define the number of rows times the number of columns, and there are 5 rows and 2 columns, and then just plug in every single number in your observed table or the table under the observed values and put it in matrix A. And then to go to matrix B, you go to second function x to the negative 1 and go to edit and go down to letter B and plug in the expected values of our computed or calculated values a while ago. So it's also 5 by 2 matrix, or basically the table of our expected values. And just like what we did on matrix A, just input all the values that you calculated from the second table, which is the expected value. And now we're ready to compute for our test statistic and p-value using our TI-84. So just go to the first screen and go to stat. And under stat, you go to test and go all the way down to chi-square test. Now there are two tests in your TI-84. We have the chi-square test and chi-square goodness of fit test. Obviously we're working on chi-square test, so just push enter, and by default the observed and expected values will be matrix A and matrix B. So all you need to do is to go to calculate, and the calculator will compute for the test statistic and the p-value of your data set. So in this case, we have our chi-square or the test statistic of 11.725 and our p-value of 0.0195 and a degrees of freedom of 4. Now sometimes on a test, you are asked to compute for the degrees of freedom, and I'm going to show you the formula in computing for the degrees of freedom for chi-square test for independence and test for homogeneity. Now going back to our table, we're going to compute for the degrees of freedom manually, and the degrees of freedom is given by the formula number of rows minus 1 times number of columns minus 1. So in this case we have 5 rows, so 5 minus 1, and 2 columns, so 2 minus 1, and multiply them and you will get 4 as the degrees of freedom, which is also here in your calculator, but sometimes on some of the tests you are asked to compute for the degrees of freedom for chi-square. So that is the formula for finding the degrees of freedom, and our test statistic and p-value are as follows. So the chi-square is already generated by our calculator as well as the p-value. So we know that at 1% alpha we are not going to reject the null hypothesis because our p-value is greater than 1%, because this one is almost 2%. So in our conclusion, we could write that with a p-value of 0.0195, which is greater than 0.01, we fail to reject the null hypothesis. So our conclusion is that there is no convincing evidence that there's a difference or a difference exists in the distribution of quality of life for heart attack patients in Canada and the United States. So at 1%, we fail to reject the null hypothesis, but at 5%, we can reject the null hypothesis, but since the problem is giving us 1% alpha, we're going to not reject the null hypothesis. So this is how we perform the chi-square test for homogeneity, which is the same as test for independence. And if you've learned something from this video, please like, share, and subscribe to my channel. Thank you.